our last method for finding volume, the cylindrical shell method, sometimes just called cylinder, sometimes just called shells. What we're looking at here is hollow cylinders. So think, the end of a roll of toilet paper, right? You got that little cardboard tube. That's what we're thinking. We're going to take little hollow cylinders like that and put one inside of another one infinitely to find the volume of a shape. So I'm going to do my best to sketch a little picture of what we're looking at here. Suppose we've just got, why I made the x-axis so big there. Suppose we got some function here. It doesn't matter what the function is, we'll just call it f of x. Suppose we're looking at it from here to here, and we're going to go around the x-axis. Okay? Now, for one, if I'm going to take this function and revolve it around the x-axis, I could just use a disk, right? If I revolve it around and slice it this direction, it'd have a thickness of dx, and I'd have a circular cross-section, and we do pi times the radius squared. Would you all agree with that? That's what we've been doing?
Yep.
Right. Yeah, so that's one thing that we could do. But we could also do it with these hollow cylinders. And so what we do is draw what we call a typical rectangle, which there's our typical rectangle right there. Very exciting. We're going to take this and make it parallel. So the length of it here is parallel to the axis that we're revolving around. So if we're going to revolve around the x-axis, we're going to make it have a height or a length here parallel to the x-axis. And we're going to pretend that it is infinitely thin in the other direction. So it has a thickness of dy. So it is infinitely thin in the y direction, which means that when we sum together, all these volumes that we're going to find, we're going to be able to do this integral in terms of y, rather than if we sliced it, we'd be doing the integral in terms of x. So that's the cool thing about shells, is it allows us to do this volume finding in terms of the other variable that we would not use if we were doing disks or washers. And so just due to the nature of some functions, it might be impossible to do this integral in terms of x. And so we could flip it around, use shells, and do it in terms of y. Does that make sense why this method is sometimes helpful and necessary? Hopefully. Right. It's going to allow us to use the other variable. And later on today, we're going to see an equation where we're going to go around the x-axis, but it would be impossible to do it in terms of x, and so we'll have to do it using shells in terms of y. So what we do is we take this little rectangle and we revolve it around the x-axis, getting a hollow little cylinder here. So imagine this is it's a cylinder that is completely hollow, that has a thickness that is so infinitely thin that we just call it dy. But because it does have a tiny thickness of dy to it, we can find the volume of that cylinder. And so the volume of that cylinder should be the lateral surface area here of it, the surface area of it, times the thickness. And so you'll see that down here. The volume ought to be the lateral surface area, which is 2 pi r times the height or the altitude. Because if we think about a cylinder, right, how do you find the lateral surface area of a cylinder? Well, you find the circumference times the height, right? Circumference times height, which is 2 pi r h. And if this is hollow, the lateral surface area times the thickness of it should be the entire volume of that cylinder. Does that make sense to everybody?
Yes.
All right, good. So what we then have to imagine is that from the lowest y value to the highest y value of this, there are an infinite number of these cylinders. And so here's another one. And what do you note about this blue cylinder that I've drawn? First off, what can you tell me about its radius in comparison to the red one?
Small.
Right, the radius is less. What can you tell me about its height?
Greater.
It's larger. So effectively, this blue cylinder is inside of the red one, but extends out beyond it a little bit, right? And if I were to draw another one, let's say down here in green, it would have an even smaller radius, right? It would be inside the blue one. I'm going to extend out beyond the blue one. And if, let's say, I drew another one up here, it would have a larger radius, but it would extend, or the red one would have extended out of that one. So we've got a bunch of these cylinders of different radii and different height sort of fitting together to create all of the space made by this solid of revolution. The best analogy I've come up with for this is if you think about, I don't know if you're familiar with them, you probably are Russian nesting dolls, right? Where you've got like that little wooden doll and you open it up and inside of it, you take the head off of it and inside of it is another one. And you take the head off of that one and inside of it is another one. And there's just a bunch of these little dolls that look exactly the same inside of one another. You guys are familiar with those?
Very.
Yeah. Oh, good. Yes. Everybody's got like 12 sets of Russian nesting dolls, I'm sure, in their house, right? That's effectively what we're looking at, except that, you know, there's one inside of the next one, except sometimes that next one extends further out because they're just hollow cylinders rather than actual dolls. Good or no? Does it conceptually make sense? So what we're going to do is we're going to just find the volume of a generic one of these and say, all right, if I can find the volume of one of those, then I can sum together those volumes from the bottom of the region to the top of the region. Or if I was going around, let's say the y-axis, I would do it from the left part of the region to the right part of the region. Everybody good so far?
Yes.
Okay, so let's try to do this with an actual function. I've stolen this picture from the book, and so it's already going to give you the information about what the radius and what the height is. But I feel like this picture is a better drawing than I could possibly ever do. So maybe it'll help you get a little bit of an idea of what these shells look like if you were still struggling visualizing. So we've taken the region bounded by the curve y equals root x and the x-axis and the line x equals 4, right? And they sort of got this projecting out at you a little bit, sort of looks like, at that region. And they revolved it around the x-axis to make a solid. And we want to find the volume using shells. Now, before we start even thinking about this, could this be done using a disk?
Yes.
Yeah, right. We slice it this way, have a thickness of dx. We do it in terms of x. It'd be the radius of that, which would just be the simple value of the function squared. You'd integrate from 0 to 4, pi times the radius squared, and it wouldn't be too bad at all. In fact, it'd be very easy. It's going to be a lot more difficult for this problem to use the shells, but we're going to do it anyway, and we'll show in the end that that it comes out to be the same. In fact, let's do it the other way real quick. It should have been, if we were doing it using a disk, right, it should be pi times the integral from 0 to 4 of our radius, which is root x squared, which would give us what? Pi x squared over 2 from 0 to 4. And what does that give us? Just 8 pi, right? So we should see that using a disk, that's very easy. Using the shells is going to be more difficult, but we should get an answer of 8 pi. So let's see if we can figure out how to make this work. Here is our typical rectangle that we've now revolved around here, right? To make this cylinder. And the cylinder has a thickness of dy. So anytime we revolve around a horizontal axis, whether it's the x-axis or the line y equals -1 or y equals 1,000, the thickness of these cylinders will always be dy, and we will have to do it in terms of y if we're using shells. Okay. The height of the shell, in this case, is from the edge of this out to the line x equals 4. So the whole thing is 4. We've gone over x from the y-axis. So the height should be 4 minus x. But since we have to do it in terms of y, we know that x is y squared, so it becomes 4 minus y squared. Does that make sense on the height?
Yep.
Okay, perfect. And then our radius, and this is the nice thing about doing shells, our radius, if we are revolving around the x-axis, the radius will always just be y. It will just be the distance from the x-axis to the function. And likewise, if I'm revolving around the y-axis, the radius will always just be x, which will be super convenient for us. So what we would do is we just follow our formula, 2 pi times the integral of the radius times the height, dy, and we'd integrate from our lowest y value. What's the lowest y value of our region?
0.
Yep. And what's the highest y value of our region?
2.
Mm-hmm. And so we'd go in. This integral is not super difficult. The setup was a little more difficult than with the disks. And the integral is a little more difficult, but still it could be a lot worse. So we integrate 4y to get 2y squared. We integrate y to the third to get y to the fourth over 4, 0 to 2. And what do we end up with? We end up with 8 minus 4 minus a 0, and we still get 8 pi units cubed. So a little extra work this time for this particular one with shells, but hopefully that gives you an idea of how we go about it using shells, and we can see that it comes out to be the exact same answer as if we had done it. Everybody good? Any questions there?
So if we wanted to revolve this figure around the y-axis instead, would we use a thickness of dx?
Exactly. Yep. You would always draw the typical rectangle as parallel to the line you were revolving around, and so that would give it an infinitely thin thickness of dx. Yep. And in fact, I think the next problem I'm going to do, maybe either the next one or the one after, we're going to go around the y-axis. So. But yep. And so if you went around the y-axis with this region using a washer, you'd have to do it in terms of y. But using a shell, you could then do it in terms of x. So that's the really nice thing about having these two different methods, the disk washer method and the shell method, is that it allows you to choose which variable you want to use between x and y, depending on the function and where you're going around and how difficult it might be each way. You can pick which variable will be easier for you. That's the nice thing about it. All right. Yeah, here we go. We're going to go around the y-axis with this one. So we got 4 minus x squared. We got y equals 3x. And we got x equals 0. And we want to go around the y-axis. And we're going to use shells to find this volume. So real quick, let me just sketch this. 4 minus x squared looks like that, right? That's not where that should be. we'll pretend that that went through the origin like it was supposed to. Y equals 3x and x equals 0. And I'm going to say this is the region in the first quadrant because there are two different regions here. So the region in the first quadrant, and there's x equals 0, right? So we're talking about this region right here. Everybody good with that?
Yes.
All right. We're going to take that and we're going to revolve it around the y-axis. So we drew our typical rectangle that we're going to revolve around that is infinitely thin in the x direction. So we'll say this has a thickness of dx. Revolving it around the y-axis, all we need to find is the radius and the height. So our radius should be easy. The radius is just this, right? And what is that value? It's a distance measured from the y-axis going to the right. And how do we measure any distance from the y-axis going to the right?
X.
Always x. So our radius is x. And like I mentioned in the last one, anytime you're revolving around the y-axis, your radius will just be x for shells. Just like if we revolved around the x-axis, our radius was y. We revolve around the y-axis, our radius for shells is x. Then we need to find the height, right? And that is our height. Well, how do we find the height? In terms of x.
4 minus x squared minus 3x?
Exactly, right? We just look at the upper bound of our region. The upper bound of our region is always 4 minus x squared. The lower bound of our region is always 3x. So the difference between them would be the height, which would be 4 minus x squared, the upper one, minus 3x, the lower one. Everybody good with that being the height?
Yes.
Good. So our integral should be 2 pi times the radius times the height dx times the thickness, right? And we have to figure out our limits of integration. Well, what's the furthest left point of our region? So we're doing in terms of x, starting at the leftmost. What is the furthest left value of this region? 0. And the furthest right x value in this region, we'll have to find this point of intersection, right? Which we'll do by setting 4 minus x squared equal to 3x, giving us x squared plus 3x minus 4 equals 0, or factoring to get x minus 1x plus 4. So that tells us they intersect twice, once at x equals 1 and once at negative 4. So this is clearly x equals 1. Yeah? Good or no?
Great.
Great. So now we have 2 pi times the integral from 0 to 1 of 4x minus x cubed minus 3x squared dx. And we'll integrate. And we'll plug in 1 and 0. And what does that simplify to? 2 minus the 1 is 1. 1 minus the fourth is 3/4. 2 times 3/4 would be 3/2. So 3 pi over 2 units cubed. Good or no?
Good.
Great. And I would say this one is probably easier using shells, because if we try to do it using a disk, it's not a lot more difficult, but we'd have to do it in terms of y. And as we go up from y equals 0 to y equals, whatever this is, 3, the linear piece is to the right. But from y equals 3 to y equals 4, the parabolic piece is to the right. And so we'd have to separate it into 2 different integrals. But doing it this way, we can do it all with one integral. Good or no? All right. Let's take a look at these two. So we want to use shells to find the volume generated by revolving the region between 2x minus 1, x equals 0, and y equals root x around the line y equals -2. So let's start with a graph. 2x minus 1, y equals root x. And x equals 0. So the region that we are looking at here is this one. And we're going to go around the line y equals -2. So when we sketch our rectangle, we need to sketch it parallel to that line. Now, this causes a little bit of an issue, because when we do this, we do it in terms of y, which means when we're doing things in terms of y, we have to look at the function that is to the right of the other function, right? And we have to see what functions bound the right and the left-hand sides of our region. So for some of the y values, the left region is the y-axis, left part of the region is the y-axis, right? But for some of the y values, the left part of it is the square root function. You all see that depending on the y value we're at, the region is bounded on the left by different things.
Yes.
Yeah, so that's going to be an issue with our height. So we'll come back to the height in a second. Let's think about the thickness, which we just said, right? What is the thickness? It should be dy. And what about our radius? Normally, if we're just going around the x-axis, it should be y, but we're not just going around the x-axis, we're going around y equals -2. So y is the distance from the x-axis up here, or potentially down here. What do we need to add to that to get the actual radius?
Two.
Yep, should be 2 because we are at y equals -2. So from 2 to y. So 2 plus y is our radius. And for a y value that's negative, like -0.5, we'd have 2 plus -0.5, which would be 1.5. And so we'd have that radius that is less than 2, and it would still work out. But let's think about the height now. So if we think about the height, from y equals 0 to y equals 1, what is our height? It's the linear one, right? Minus the root function. it's the x value of the linear one minus the x value of the root function. But it's got to be in terms of y. So the x value in terms of y of x equal or y equals 2x minus 1 would be x equals 1/2 y plus 1/2. And the x value of y equals root x would be x equals y squared. So our height should be 1/2 y plus 1/2 minus y squared. Everybody agree with that from y equals 0 to y equals 1?
Yeah.
What?
I just was asking if everybody agreed with that. You guys all agree with that or no?
Wait, can you re-explain where you got that height from again?
Sure. So the height is the distance from here, from the y-axis to the linear piece, minus, I shouldn't have drawn it that far up. It's, all right, I'm gonna sketch it larger down here. So up here, the distance, this height right here, is this length minus the length from the y-axis to here. So it's the length from the y-axis to the linear piece minus the y-axis to the root function. Does that make sense or no?
Yeah, it does.
Right, so it's this x value minus this x value. And this x value is 1/2 y plus 1/2 from here. And this x value is y squared from the square root function. Any questions on that? Or everybody good there? Okay. And then from y equals -1 to y equals 0, our height should be just the linear piece minus 0. So 1/2 y plus 1/2. Good or no?
Good.
Okay. So in order to do this using shells, we'd have to set up two different integrals. One that would be 2 pi times the integral from 0 to 1 of our radius, 2 plus y, times our height, 1/2 y plus 1/2 minus y squared dy, plus 2 pi times the integral from -1 to 0 of that same radius times this 1/2 y plus 1/2 dy. And I'm not going to bother to go through and distribute all that out. That's a bunch of algebra and some fairly basic integration once you distribute it out that you should all be able to do. Conceptually, everyone okay with that setup though?
So even when we're doing integration by shells, we should still pay attention to like right functions and like what's on top, what's on bottom.
Most definitely. Yep, you still got to focus on that because you got to use that to find your height most of the time. All right, the second part of this is now asking, what if we revolved around the line y equals 5? Well, if I revolve around y equals 5, is that going to change the thickness of these?
No.
No, should still be dy. Is it going to change the height?
No.
Right, 8 should be the same, right? Should be the exact same heights. But it will change the radius, won't it?
Yeah.
So what should the radius become?
5 minus y.
It should be 5, the distance from the x-axis to y equals 5, minus this little y piece that we've gone up. So the only thing that will change is 2 plus y becomes 5 minus y. Everybody good with that?
Yes.
Cool. And once again, I'm not going to force us to multiply that all out and do all that arithmetic. We'll do it for the next problem. But any questions on that? All right. The last page of official notes of new material for this year. And we've got 34 minutes to get through. I think we can do it. So we want to use shells to find the volume of the solid generated by taking this region between the y-axis and 12 times y squared minus y cubed. So that's this region right here. And we're going to revolve that around the x-axis, which means we're going to draw a rectangle parallel to the x-axis and revolve it around that x-axis. Everybody good with that conceptually?
Yeah.
Okay, perfect. So if we're going to do that, first off, what is the thickness going to be?
dy.
It'd be dy, good. And what is our radius going to be?
Y.
Should just be y, good. And so all that's left then is our height. Well, what's our height? Our height is the distance from the y-axis to some value over here to the right, which is just x, isn't it?
Yes.
Or in this case, 12 times y squared minus y cubed. And we should be able to just go in and integrate. And I'm going to pull this 12 out with the 2 pi's just to make it a 24 pi out in front. And we'll have y times y squared minus y cubed dy. And we're going to integrate from the lowest y value, which is 0, to the highest y value. What are the coordinates of that point? It's 0, comma, what? What y value makes this 0? Yep, 0, 1. You should be able to just see 1 squared minus 1 cubed, right, is 0. So 0, 1. And so now we'll distribute that y through, y cubed minus y to the 4th dy, giving us 24 pi times y to the 4th over 4 minus y to the 5th over 5 from 0 to 1. And what is a 4th minus a 5th? Should be 5/20ths minus 4/20ths, which would be 1/20th. Which if we divide those each by 4, ought to be 6 pi over 5 units cubed. Good or no? And if I tried to take this and revolve it around the x-axis, and let's say I had attempted to slice it vertically like that, I would have to do everything in terms of x, wouldn't I?
Yeah.
And what would the outer radius come from? It would come from this function, right? It'd be the y value, my outer radius up here. What would the inner radius come from? It would come from the same equation, wouldn't it? Wouldn't my
Oh, yeah.
yeah, and that would be a major issue. And beyond that major issue, if I'm looking at this equation, if I have to do it in terms of x, I'm going to have to solve x equals 12 times y squared minus y cubed for y and put it all in terms of x, which is not something that I think we are going to be able to do. So there is no way to solve this for this volume to do it in terms of x. It's got to be done in terms of y.
Who texted you?
What was that? Is that a question for me or somebody yelling at their parents? I don't know. Who knows? So there's no way to do this in terms of x. It has to be done in terms of y. Good or no?
Yeah.
All right. Now, what if we were to revolve this around the line y equals 1? Would the thickness change?
No.
No. Would the radius change?
Yes.
Yes, it should, instead of just being y, the radius is now this distance, right? Which would be 1 minus whatever y value I've got up. If that's y, the radius should be 1 minus y. What about the height? Does the height change?
Nope.
Height stays the same. So I should, again, be able to set this up as 2 pi times the 12, 24 pi, integral from 0 to 1. Now it's 1 minus y times y squared minus y cubed dy. And we can, oops, I forgot my pi. We can distribute that all
What?
out. I just said I forgot my pi. We're going to distribute it all out now. Y squared minus 2y cubed plus y to the 4th dy, which we should be able to integrate. And what does that give us? Y cubed over 3 minus 1/2 y to the 4th plus y to the 5th over 5 from 0 to 1. And when we plug in the 1 and the 0, what do we get? We get 24 pi, 1/3 minus 1/2 plus 1/5 minus 0. And what's our third? 1/3 minus 1/2 should give us what? Negative 1/6. So we've got 1/5 minus 1/6. And 1/5 minus 1/6 ought to be 6/30 minus 5/30, which should be 1/30. So we got 24 pi over 30. We divide those both by 6. We ought to get 4 pi over 5 units cubed. Good or no?
Good.
Great. All right, last problem. We go around the line y equals 8/5. That's going to be even further up here, right? And if we go around that line, what's going to change? Is the thickness going to change? No.
Nope.
Is the height going to change?
No.
Nope.
No, it should stay the same, but the radius will change, right? The radius will become, instead of 1 minus y or just y, it'll become 8/5 minus y. So we should have 24 pi times an integral from 0 to 1. Got to make the arithmetic a little bit annoying on the last problem that we're going to do. 8/5 y squared minus a y cubed and minus an 8/5 y cubed would be minus a 13/5 y cubed plus y to the 4th dy. And when we integrate that, should be 24 pi, should be 8y cubed over 15, should be minus 13 y to the 4th over 20 plus y to the 5th over 5 from 0 to 1, which ought to give us 24 pi times 8/15 minus 13/20 plus 1/5 minus 0. And the common denominator there would be 60. So that'd be 32/60 minus 39/60. That's negative 7/60. And then negative 7/60 plus 12/60. That'd be 5/60. And 5 over 60 is 1 over 12. So we get 24 pi over 12, which is 2 pi units cubed. And apparently my computer still wants me to activate Windows. I assume you guys can see that too. I've been trying to do it, but it won't let me. And that's it. Any questions there?
I think I'm probably just missing something obvious, but when you revolve this around the y equals 8/5, shouldn't it end up looking like one of those washer things? Like where you
Yep.
have to do like one radius minus another?
I mean, it does end up looking like one of those, but it doesn't mean that you have to do it that way. You can do it with shells, or you can try to do it using washers, right? So you'd end up with some, thing up here like this, and you'd slice it, right? But the problem, like we were saying earlier, is that the outer radius of this and the inner radius are both derived from the same equation. That they both come from x equals 12 times y squared minus y cubed. And to do it in terms of x, if we sliced it that way, we'd have to solve this for y, which we're not able to do. And so we can't even use the washer method because this equation is not able to be explicitly solved for y.
I see. So those two methods are completely separate. I processed that now. Thank you.
Yeah, I mean, you can use either one for any problem as long as the equations and the variables allow you to. Does that make sense? Yeah, so I mean,
Yeah.
Theoretically, we could have used washers for this one if this equation allowed us to, but it didn't. So like back here, when we did this one, there was a giant pane. We revolved it around this line. We could have used washers for this one, and it actually would have been quite a bit simpler, right? We could have sliced it this way and got an outer radius and an inner radius and been just fine. Right. Similarly, like to the first one, right? We could have sliced it and we did discs, like, and we did do the disc. We can do it either way if the equations allow. Does that make sense to everybody?
Yes.
I have a question. So if you can't convert the equation to y, and on the AP exam, all you have is a graphing calculator, how do you graph it?
If you can't, generally they'll give you the graph if it's something that's fairly complicated like that. But the only other way to do it, if you don't just know what the graph looks like, if it's something like x equals y squared minus 4, those you should be able to convert back and forth. But if you can't convert, you can always just plug in some points and try and figure out what happens. I mean, x equals 12 times y squared minus y cubed. That's a cubic. It's just a cubic that's been flipped over. So it should look like a cubic of some sort. And if you can plot a few points, you should have a general idea of what it looks like. I mean, in addition to that, you could always take the derivative of it, dx dy, with respect to y, and then find this is not something for this class. You could take the derivative of it and find where it has a maximum x value and a minimum x value and plot some points in it that way. But generally, if it's a fairly complicated equation, they'll give you a graph, and if it's not, they won't. This one, they would probably give you the graph of it. I would be almost positive that they would.
Okay.
Yeah. That, I mean, the best bet if you don't know what it looks like is just plot as many points as you can. Any other questions?
So even though like volume by shells isn't like for Calc AB, can we still use it on the free response if we can?
Yes. You are welcome to use it. And like I said, every once in a while, they'll put a problem up there that would be a lot easier using shells. And you're welcome to use it. You don't even need to indicate that I'm using, you don't even need to say using cylindrical shells. You can just use the formula and put in your radius and your height and your thickness. And if it's easier, do it. And that's totally fine. Other questions?